so much for inviting me. I'm going to be talking about data lakes, and so the slide here says the future of data lakes, and that is the title of this session. But I'm going to talk a little bit about related concepts as well, like data warehouses, data lake houses, the history of all of this, just so everybody has a good idea of what data lakes are and where things are headed. So with that said, let's jump into things. So yeah, we already established that. My name is Danny. I am currently the head of data and marketing and a little bit of partnerships as well at Estuary. Before that, I used to work as a data engineer for a decade, pretty much. And I worked as a data engineer at startups, enterprises, and most recently, I did a bunch of years in consulting, where I eventually led another team of data engineers. So throughout this journey, I had a chance to work with a lot of amazing people and a lot of amazing technologies as well, a lot of data lakes, a lot of data warehouses. So most of the information distilled in this short session will be based on my experience with these tools. So what exactly are we going to talk about? The way I imagine this 1 hour is that I'm going to talk over a few slides for roughly 30 minutes. Then I'll show a live demo of one data lake house implementation using DuckLake. So y'all can see an actual data lake in action. And then after that, we'll have, as Chloe said, like 15 minutes dedicated for Q&A. So throughout the session, if you have any questions, then please send it over in the chat. And yeah, we can discuss anything I say at the end. So in the actual session, we're going to talk about, as I mentioned, data lakes, warehouses, lake houses, open table formats, Iceberg, DuckLake, what these mean at all, how do they actually come together to form a cohesive data stack that enterprises use for analytics and a bunch of other purposes. And yeah, there's a lot here, and we don't have an infinite amount of time, so let's jump into it. So in order to understand the future, a wise man once said that we have to go back in time. I couldn't find any truth that he actually ever said this, but it was a very fitting quote to kick off this presentation. So because that's exactly what we are going to do, and I'm pretty sure people didn't have data lakes in mind when he said this. So in order to understand data lakes, let's take a look at a little slice of data infrastructure history. So the three main versions of a data processing unit that are relevant to data lakes are data warehouses, data lakes themselves, and most recently lake houses. Data warehouses were the initial first idea on a solution for analytics. Before that, there were operational databases, and operational databases were and still are the backend for applications. These databases are not made to handle the types of queries that you would write when you're analyzing data. They are made for handling a large amounts of writes, individual updates to certain records, and they also don't plan on keeping history of these changes. So all of these challenges gave birth to data warehouses that had a better handle on these things. They actually stored historical data and a lot of other stuff that we'll jump into in 1 second. So data warehouses also had their own challenges, which made sense because they were very similar to databases, the original databases, operational databases. And during the 2000, the year, or during the 2000s, there was the so-called big data boom. That's where everybody started. That's where everybody realized that they have a lot of data that they don't know what to do with, but they understood that it's valuable. So we needed a solution to actually collect all that data. And it can be unstructured, not just structured. People started recording videos constantly, recording audio, images, all that stuff. And yeah, data just started to exponentially increase in the world. And we needed somewhere to store that. So data lakes were the solution for that, which separated the storage out into its own component. And we were closer to solving the scalability issues, but we still needed a solution on how to actually connect this data, all this unstructured data, with some kind of compute that lets us run analytics on it. And that's what gave birth to lakehouses and open table formats as well. And the combination of these make up most of the popular data architectures that exist today. So to dive a little bit deeper into each of these, data warehouses are probably something that most of you are already familiar with, so I won't spend too much time on this. But this was as I mentioned, the original solution to the challenges of only having operational databases. We needed something for analytics. We needed something to store historical data, but yeah, these still had coupled storage and compute, which made the whole thing very hard to scale. Like even if your data scaled and you were collecting a lot of historical stuff or just generating a lot of new data, you had to add new machines to your cluster, and yeah, it was just a nightmare. Also, these data warehouses were using disks as storage, which are expensive and also hard to scale. So there was not a lot of flexibility, in terms of scaling here, and also not a lot of flexibility in terms of unstructured data. These data warehouses were only meant to hold structured data. So even if you extracted some data from a source, you would still have to bring some structure to it before you load it into the warehouse. This is commonly known as ETL. So if you're a data engineer, you have probably written ETL pipelines yourself, and you know that there's always some kind of transformation that you have to do before the data lands in a warehouse. So yeah, one thing that they did well, though, is that they supported SQL, which essentially became the de facto language of analytics with the rise of data warehouses. So all of those scalability and flexibility issues, as I mentioned, were enough of a reason to try to come up with a new solution for them. And that new solution was data lakes. So data lakes are storage layers that store even the raw unprocessed data from any sources that you can imagine. And it supports unstructured data, most importantly. So you can imagine that all the files that you have, all the videos, all the music, all the images, all the JSON files, anything that you can think about can all just be dumped into one data lake, and you can figure out how to deal with it later. The goal with these data lakes was to have a place where you can collect and store all of your data cheaper than a data warehouse. Because with databases, you would have to conform to a certain structure, but with data lakes, you can just store the files in some kind of file hierarchy. And yeah, you can just use a basic file system or later an object storage like Estuary, which is a lot cheaper than having to use disks. Yeah, so also one of the biggest use cases for data lakes was machine learning and real-time processing of data. Feeding the initial machine learning algorithms, not necessarily these large language model ones, were a better fit for this type of data storage than traditional data warehouses. One negative of data lakes, well, there's a few negatives, but one of the negatives is that it was not really good at SQL. So actual analytics on the data became a little bit more complicated. And by little bit, I actually mean a lot more complicated, but more than in a few minutes. So data warehouses, data lakes, and then finally the best solution that totally makes sense and solves all the issues, solves all the compute, and solves all the storage issues is data lake houses, right? So lakehouse itself is a term coined by Databricks, the company Databricks, based on their initial architecture that they came up with for their platform. And they actually have a very good white paper about the lakehouse architecture itself. So it's a super easy read. If anybody's curious, I really do recommend it. It's only a few pages, but it's a great overview, and it's not necessarily tied to Databricks itself, the platform. So yeah, data lake houses, the silver bullet, it does everything. Storage is cheap. You can use object storages. It's perfect for BI tools, machine learning tools, streaming data. Yeah, it is definitely the goal, as it turns out. But how do we actually get there from a data lake? So data lakes, as I mentioned, they suffer from many issues, some of which are there on this slide. But yeah, so data governance and quality, obviously a very hard solution to tackle. And with a data lake where you can just dump in any kind of data that you see, you can imagine that there's inconsistent data types, lots of missing fields. Data lineage was not really a thing with data lakes, so discoverability was completely, it's a horrible experience. And in general, it was hard to ensure data correctness and compliance. There were a lot of issues with reliability and consistency. Data lakes by themselves, they don't support ACID transactions. So it could happen that there were partial writes for data sets. Data could get easily corrupted if you were doing concurrent jobs, which you were probably doing if you had more than 2 people working on the same data set. You could also see a lot of inconsistent reads, which means that downstream jobs that read the same data could actually give different results, which is definitely not something that you want to encounter in analytics. And all this made for a horrible experience when you try to roll back data or try to fix any issues. And given the fact that data lakes were trying to solve for scalability first and foremost, they still suffered from a lot of performance limitations. The large data sets were like hard to query because of how the data lake was implemented. There was no notion of partitioning or indexing, or even if it was, you had to write it yourself, and that's super complicated. So you had to like scan complete data sets to get a small piece of it, which is something that you should never do. So the whole thing was hard to use and very expensive, or some of the queries that you wanted to run turned out to be very expensive. So in general, there was like a lot of operational complexity around data lakes. All the workflows became super fragmented because you had to use like 10 different tools bundled together with duct tape just to make a simple query work that you can actually use for analytics. And even though we tried to solve for streaming workloads as well with some tooling, it was very hard to integrate any kind of real-time data processing with data lakes and batch data together. So all of these and many more created this idea of data swamps, which were the results of unmaintained, unmanaged data lakes. And it was very hard to avoid. your data lake becoming a data swamp. So the biggest question is, once you're there, how do we drain this swamp? But probably the better question to ask is like, how do you avoid our data lake becoming a swamp? And one of the answers that turned out to be working really well is table formats, using table formats. So table formats are not necessarily a tool, they're more of a specification with different implementations that help you bring some structure to your data lake or your data swamp. So one of the most popular early table formats was Hive, Apache Hive, which created a separate metadata layer on top of your existing data lake, which enabled all the things, well, not all the things, but it enabled some of the things that data warehouses had because of their structuredness, but data lakes never really had because of how open they were and unstructured. So if you added the table format, suddenly you could use SQL to query those files in your object storage in your data lake. You could implement partitioning, which is very useful if you want to avoid data with some of your large queries with partition pruning. You could integrate your BI tools straight to your data lake through this table format, because they were able to understand that those blobs and files scattered around in an object storage actually compose some kind of tables, and which have columns and schemas, and these metadata or these metadata layers stored all that information. So yeah, Apache Hive was pretty much the first one. It was fairly widely adopted during this time. It supported most of these features, but it didn't come without its own issues. So it kind of turned out that table formats are maybe not the best solution for this, because they were still like, there were some proprietary table formats, or even the open ones like Hive were like very tightly coupled to specific compute engines and other parts of the data stack. The support that they had for transactions were limited, and was limited, and it sometimes it caused more issues than actual help for you. Schema evolutions were still a horrible thing to deal with. Transactions were like not fully implemented, and yet still ran into a lot of issues. You still couldn't really do proper real-time and batch combined workloads, and performance issues still omnipresent. So if not table formats, then what is the solution? Well, where the industry is currently going is rather than looking for something completely new, is another iteration of table formats. So there, in the past few years, after this first generation of table formats that I introduced now, there has been the second generation, which you are probably some of you are probably more familiar with, like Iceberg, Hudi, and Delta. So these new open table formats, they learn from the previous table formats mistakes, or most of them. They are defined on open standards, on how files should be organized in your data lake and how metadata works. So they essentially bring real data warehouse level reliability to your data lake, while you can keep the costs still low, because all your data is still just in an object storage. So these table formats, they enable ACID transactions, schema evolution, time travel, all kinds of cool features that only data warehouses had before, and the previous generation of table formats still lacked. So these new open table formats, they do a fairly good job of bridging this flexibility and low cost of lakes with all the governance and performance power of the data warehouses. Oh yeah, I have this slide to show how the timeline looks like for open table formats, and it only goes up to 2023, but there definitely should be another portion there for DuckLake, but I'll talk about that in a few slides as well. So yeah, you can see that we almost are in 2 decades of evolution at this point, from the first data lakes and the open table formats. So there has been a lot of development, and I think there's going to be no stopping anytime soon. There seems to be a few technologies that the industry is converging towards, namely Iceberg, but there are still new table formats coming up on the scene. So it's definitely an interesting period. So yeah, as I mentioned, Iceberg is one of the more popular ones, and let's talk a little bit more about that. So Iceberg itself is similar to Hive, Apache Hive, that I talked about a few slides ago, in the sense that it is also a table format that works with a data lake under the hood. Data lake being your files in some kind of file format, organized in a hierarchy in some kind of object storage like S3. So Iceberg itself came out of Netflix. They were a team there was their initial developer, who eventually founded Tabular, the company, and they were the largest contributors to the Iceberg specification. And I think last year, they got acquired by Databricks. So weirdly, that kind of makes Databricks now the largest contributor to Iceberg, which is weird because Databricks had their own table format data lake for a long time now. So it's an interesting situation there. The bottom line is that everybody seems to like Iceberg. It is very well received. It has a very broad integration spectrum by now. All the popular data warehouses like Snowflake or Databricks, as I mentioned, or even AWS through Glue has some level of support for it. So the industry is definitely seeming to converge around it as like the storage layer, or the table format of the storage layer. So yeah, Iceberg itself is a great solution. It's meant for petabyte scale essentially, but it also works for smaller scale data workloads, which some of the previous attempts at solving the data lakes issues could not say about themselves. So Iceberg itself has a great job of managing ACID transactions compared to Hive tables. It has a great implementation of snapshot isolation. So you can have any number of jobs that read or write the same data, and they won't mess up each other's work at all. So if you have like streaming workflows, this is super important. With other table formats or previous table formats, this is not something that you could achieve. It also has a great solution for schema and partition evolution. In other or previous table formats like Hive, even changing like the type or the name of a column was a gargantuan task. And with Iceberg, it really feels like just doing it in a data warehouse, where you just write a statement to change the name of this column to something else, and it happens, which is something that you were not able to achieve with previously. It also implements time travel, which is super important for rolling back data or looking at the previous state of a data. If you want to look back in time, it can be for debugging issues, or it can be for analytics as well. And one of the best features, I think, is hidden partitioning for Iceberg. which means that you don't have to care where your data is physically stored. So Iceberg completely handles that for you. And you just get the performance benefits of partition pruning when you write a query. And yeah, as I mentioned, the Iceberg, it came out of Netflix, and Netflix deals with a lot of data. So the core idea was to solve their scale first, but it turns out that all these decisions that they made with Iceberg's architecture actually works for smaller scale as well. So Iceberg itself, as a table format, it seems like it's the winner in the table format wars out of the other options, purely based on popularity, I would say, and the level of integration and adoption. So with Iceberg, you can really plug and play what kind of compute engine you want to use for your transformations. It works with streaming stuff like Flink. It works with Spark. It works with Snowflake. It works with Databricks. So it works with DuckDB. Really, any compute engine you find is best for your specific use case will work with an Iceberg storage, which is great, because you don't necessarily want to be tied down to one specific compute. It might be too expensive for your use case. It might not do real time. So yeah, this is one of the best features of an open table format. There's a lot of managed services for Iceberg lately. So you don't even have to try to ship or deploy your own. You can just use Snowflake. It has managed Iceberg tables, or AWS has managed Iceberg tables as well. So lots of options there, which is helpful as it lowers the barrier of entry. And it has a super active community. Like not only Databricks is adding new stuff to Iceberg, you can get involved. They have a very active Slack workspace as well that anybody can join, and there's always interesting discussion going on there. Yeah, and everybody's, or not everybody, but a lot of people are implementing and adopting Iceberg. I work at a company who does data integration, and we see more and more people even starting from scratch that want to use Iceberg, and a lot of people switching from data warehouses to Iceberg while keeping some of the compute on the data warehouses that they used before, just to keep costs down and make sure that they actually own the data themselves. So yeah, Iceberg is definitely a great option for data lakes, but it still doesn't necessarily. It's still kind of hard to get into. There's a lot of moving pieces. You have to know and understand a lot about it to make it work. So there's always room for simpler solutions. And one of these simpler solutions is DuckLake, which is a lightweight alternative, I would say, to Iceberg. It has a little bit of a different architectural design than just being a pure table format, as it actually brings the catalog itself and bundles the catalog and the metadata about tables and the schemas and everything else is not stored in files in your object storage, in your data lake, but in a separate relational database. So it was developed by DuckDB, DuckDB Labs, and mainly firstly designed for embedded analytics and local processing, but I'll show you an example of how you can actually use it to do analytics in your team. It doesn't necessarily have to be local. The DuckDB implementation is actually just one option to use. In the future, any database can serve as the backend for the metadata store. It's not necessarily tied to DuckDB. It's just the first one that they implemented. So DuckLake is pretty cool. It's fast. It's super simple. It's way simpler to get started than Iceberg, and it works really well for small to medium data sets. which is DuckDB's niche for now. But given that they are adding a ton of new features lately, I would expect that to expand as well to proper large data sets too. So to summarize, like the key differences between Iceberg and DuckLake. DuckLake is for simplicity and the SQL first design in terms of the metadata store, ideal for smaller scale workflows, while Iceberg is more battle tested, supports any kind of compute engine that you can imagine, and is really ready for mission critical petabyte scale workloads. Yeah, so to summarize the important thoughts so far, I would say lake houses are definitely the future of data lakes, and this true separation of compute and storage with a table format in the middle seems like a winning architecture, because it works for 99% of the use cases. It works for streaming, it works for batch, works for any kind of analytics. The goal, I would say, is now to figure out how you can make it simpler for people to get started. For which DuckLake is definitely on the right path. So yeah, as I mentioned, I did prepare a short demo of DuckLake, because there are a lot of demos about Iceberg out there. So if you're interested in that, I think you can definitely find a few interesting ones. But there's not so much about DuckLake yet, purely because it was released only a few months ago. So what I'm going to show you is this very simple architecture of a data lake / data lake house. As you can see here on the left side, we have a Postgres database that there's a data generator script running, so it's constantly being updated with data. And I'm using Estuary to move that data in real time into a data lake in the form of Parquet files that get saved in an S3 bucket. And this will serve as a data lake in this little project. And I want to show you how you can actually query this data through either MotherDuck, if you want to go for a more cloud-based approach, or from DuckDB if you want to work in your local development environment. So I'm just going to share my whole desktop so it's easier to give a walkthrough. All right, so if you're not familiar with Estuary, I'm just going to quickly show so you can see how the ETL part works. Here I have a connector that is extracting data from a Postgres, a Google Cloud SQL Postgres database, and as you can see, we are reading almost like 100,000 data 100,000 records every hour, and those records are being written into this shipments collection inside Estuary. And if I scroll down here, I can give a quick preview of what the data looks like. So it's supposed to be realistic looking shipments data, meaning that we have fields like city, created at, location, coordinates, name, delivery names, all kinds of stuff that we can that we want to use for analytics in our data lake. So yeah, this collection is being filled up in real time by Estuary, and we are gonna, as I mentioned, move all of this in real time as well into a data lake. So I already have a MotherDuck connector live here that is hopefully working and pushing data into an S3 bucket. So as I mentioned, the big difference here is that we're using DuckLake and not DuckDB or not MotherDuck or not an actual data warehouse. we are storing our data or pushing our data into S3 as Parquet files first. So I do have that open right here. I can show you that there is this S3 bucket that I have called shipments. And let me just refresh to see if we are actually receiving data live here. So you can see that there's a bunch of Parquet files here, which is exactly what we expect. And if I go to the last page, I can see that the last Parquet file was added in my time zone. It's 1:41 now. So yeah, around a minute ago, which is great. So that's exactly what we want to see. Data is being written into sorry, I don't think this preview thing should show. Anyway, so data is being written into my data lake. And yeah, the big difference is that in order for me to query the data here, I need to create a database, a DuckLake database in MotherDuck. So if I switch there, let me see if I can zoom in a little bit. Yeah, just to make it a bit more readable. So in MotherDuck, I create a new database with the type of DuckLake and the data path set to the bucket that I showed you, the Estuary bucket that I just showed you with the Parquet files. So the thing that happens here is that MotherDuck will actually create this DuckLake database, which is not a native MotherDuck database, because it stores all the data in an Estuary bucket that I own and not MotherDuck. The thing that MotherDuck does for me is that they manage the catalog itself, the metadata store. The metadata store is this database that stores all the information about what makes a Parquet file or a set of Parquet files a table. Like if I write a SQL query, that metadata store helps translate the SQL so it can get the data from these Parquet files. Yeah, the only other thing needed on the MotherDuck side is to set up a secret so it knows, or it is able to access the actual data in S3. So I can show you how the data looks like. Let me just run this query again. And if you remember the JSON snippet that I showed earlier, this is the table version of that loaded into MotherDuck. So all the same fields, properly formatted with proper data types. I think if I look here, yeah, these show the data types as well. And this has data types because DuckLake, the metadata store, stores these data types when Estuary writes the data into MotherDuck. So if I actually run the count query, let me see, it's like 86,396 records. And if I run it again, it's still the same. Let me see if it's actually, maybe it's, all right. Okay, maybe it's not loading any data at this moment, but I didn't pray enough for the demo gods. But anyway, so this is what the table looks like. And the cool thing about this is that because it's so decentralized and all my data is in this data lake, I don't necessarily have to use MotherDuck here to access it. I can also just jump into the command line where I have a DuckDB, local DuckDB running. And all I have to do is attach the metadata store. So this is the actual metadata database that is managed by DuckDB that contains all the metadata about my DuckLake table. So if I attach this to my instance, my DuckLake instance, which fails because I already ran this command, but it's totally fine, I am now able to access that table just as I was just as I was doing it from actual MotherDuck. So if I run this query here, it shouldn't take too long. Yeah. Well, I don't know what's taking so long. Definitely, there's not that much. Okay. It's probably my Airbnb internet. So sorry about that. All right, there we go. So we managed to query the exact same database that I was querying from the mother duck instance, just by attaching the DuckDB or the mother duck metadata database. So yeah, I think that showcases how modular this architecture is and how easy it is to get started. Like creating the database here in mother duck was literally 4 lines, and yeah, you load it with data from Estuary or any other tool, and you're pretty much good to go. So yeah, that was a demo that I planned. So let me just stop sharing my screen and see if there were any questions. Should I read out the questions, or is there anyone who wants to talk about anything?
Let me jump in because I see some. Oh, I had a question and I saw another one just come through. First of all, thank you for the demo. That was really enlightening. It's kind of, we hear a lot of these terms get thrown around on LinkedIn and stuff, and it can be tricky to actually connect them sometimes to the real tech. So I appreciate the demo and all that. I was just curious, you had on the screen at one point a grouping of Iceberg, or a grouping of table formats, I think, and you had them as like generation 1, 2, and 3. How do you define those breaks?
Yeah, so generation 1 was, let me see if I can just quickly bring up that actually, so everybody knows what I'm talking about. This one, right?
Yeah.
Yeah, so the first generation are like literally the first table formats. Like Hadoop had a built-in table format, and Hive was the first, the first more popular one that people actually started to use to handle the inherent limitations of data lakes. Like data lakes without the table format are just a bunch of files in an object storage. And this first generation was like really the first try on making sense of these random files. But yeah, they just turned out to be impossible to scale and fix. So people just decided collectively to kind of leave them behind and just go for the second generation, which is Iceberg, Hudi, and DataLake. And these were the ones that started as like open, or not started, but became very popular as like open standards. So anybody could contribute. A lot. It was more inspired by data warehouse functionality, their features, and not just trying to take the fires out that data lakes had. The third generation, I would say maybe it doesn't really make sense to separate them into its own generation. Are like Xtable and Uniform, which is both are about compatibility across open table formats. So people realize that if you have data in one open table format somewhere, but use another table format in another place, ideally you would want to be able to join them without having to do some crazy amounts of ETL. So why not use the best table format for the best or wherever it's applicable? And Xtable and Uniform are these translation layers between Iceberg and Delta. So you can write a query or use a compute engine like Trino or Flink, and it doesn't matter if your data is in DataLake or Iceberg, because Xtable will translate or create this compatibility layer. So it's even an even higher level of abstraction above these second generation table formats.
Gotcha. Okay. Yeah, I was just curious because I know you mentioned in the call, and I've seen this as well, that Iceberg is certainly one of the most popular formats now, if not the most popular. And I was kind of wondering why I hadn't heard of any of those third gen tools. And I was wondering, is there anything, would you tell anyone to skip Iceberg and jump straight to that generation? Or do you feel like most teams who implement this should use something like Iceberg or even DuckLake?
I would recommend Iceberg or DuckLake. I think those are still for more complicated use cases where you already have Iceberg in place, and well, there's these very large or data teams that have Snowflake, they have Databricks, and they have all kinds of things in different parts of the company, and they need to bring it together. That's where those solutions shine for now. But I would say just getting started, Iceberg or DuckLake are perfectly fine.
Cool. Okay. And then there was one other question, and I kind of want to expand on this one a little bit. But to summarize what you showed us, it seems like basically DuckDB is running locally, but you can query it like SQL, and it's running basically like read parquet functions on the back end under the hood, and that's how the whole system works.
So kinda, yes. It does a lot more. So it has a whole database that stores metadata about what it actually means that you have a table. So it does read the Parquet files itself, but it needs to know what or which Parquet files to read and which columns to read from which Parquet files. So all the information about that is stored in the metadata database. And with the DuckLake extension, DuckDB is able to read the metadata database, which tells it, okay, so this query, this select query, you will need 3 Parquet files in these paths on S3. So it grabs those, and the extension just helps read those files.
Gotcha. Okay. Well, thank you. Those are all of the questions sent in the chat. If anyone else has any other questions, please either unmute now and feel free to jump in, or drop them in the chat.
Yeah. Now or never.
Yeah.
Yeah, sorry, I was trying to type into the chat. I have a question. So you mentioned, well, first of all, thank you very much for the talk. Thank you for it was enlightening. You mentioned DuckLake would be suitable for small to medium data sets, and Iceberg would come up at a greater scale. Do you have some rule of thumb, at where that boundary of scale is? Is it in, tens of billions of rows, petabytes, or how do you approach that decision boundary?
Yeah. Well, based on what I talked with the Mother Duck guys who work there and work with DuckLake, I would say if you're dealing with like tens of terabytes of data or hundreds of terabytes maybe, then DuckLake is not a good solution yet. In that case, I would go for Iceberg, but purely because it's such a new, DuckLake is such a new technology that they still need to iron out some of the details to handle those data sets. If you're dealing with like petabytes, then I would say like obviously Iceberg is the default. If you're on like the hundreds of gigabytes level, I think you can give it a go. I think DuckLake could really shine there, and you can help the development team out by finding edge cases.
Thank you for that clarification.
Anytime.
Cool. Do you have any closing thoughts or any advice for anyone who's trying to get started with a lakehouse?
Yeah, I would say spend some time exploring it. If you're thinking about going for a data warehouse or buying like Snowflake or something like that works out of the box, just spend a few days and look at a bit more technically involved lakehouse as an alternative like DuckLake or Iceberg. You'd be surprised how easy it is to get started, even compared to something like Snowflake, and it's definitely worth in the end.
Great. Well, thank you so much, Danny. This is awesome. And when we'll have the YouTube link up in about a week or two, so I'll send you that, and then everybody else on the call will receive it, so you can always go back and as you're practicing working with data lakes. Thank you so much, Danny, and we will see you guys all next week. Have a
Awesome.
great rest of
Thank
your
you so
day.
much.
Before we all break, I just want to give a quick plug for Database Tycoon. So we are a full service data agency, and we've been having a lot of fun hosting this summer camp series, and getting to hear from all kinds of experts throughout the industry and talking about different areas. And we're working on implementing all of those tools as well. So we're actively working on learning about how to connect them and make better pipelines for teams, and we want to hear from you. So please feel free to reach out on LinkedIn, on YouTube, anywhere you can find me or the team, and let's chat about some data problems we can solve. So anyway, hope to see you again for the next one, and have a good rest of your day. Thank you.